Good morning. So in the last video, we had discussed regarding semi-custom and full custom ICs as well as the ASIC and application-specific standard products. So like in that context, so next concept is the programmable logical devices. So these programmable logical devices, so-called PLDs, are the components so which are used to build reconfigurable digital circuits. So when compared to the normal ICs, 74 series ICs, so what we are familiar with like AND gate, OR gate, XOR gate, etc. So the functionalities of those ICs will be fixed. Okay. So for example, OR gate can only perform OR function, AND gate can only perform AND function, NAND gate can only perform NAND functionality. So when compared to these fixed ICs, so these PLDs can be reconfigurable even after manufacturing. Okay. So a PLD has a undefined function at the time of manufacturing. So before the PLD can be used in the circuit, it must be programmed or reconfigured. So by using a specialized program. So we have various types of programmable logical devices. So for example, this PLA and PAL and generic logic array and CPLDs. CPLD stands for complex programmable logical devices. And in case of VLSI design also, like we have seen this field programmable gate array, which has got programmable interconnects and logical blocks, also called as configurable logical blocks. Okay, so we have these as the different types of programmable logical devices. And for your syllabus, you have this programmable array logic. Okay, PAL 16L8 and PAL 16R8. So we have the architecture and implementation of various logical equations using PAL 16L8 and PAL 16R8. Okay. So these PLDs can be programmed after manufacture so as to vary their function. Okay, like as we know that any Boolean equation, any logical function can be implemented on this PAL. Okay. Higher unit cost than ASIC. So when compared to the ASIC design, so these PLDs have higher unit cost than ASIC and lower NRE, non-recurring cost will be low, like in case of these PLDs. And these PLDs are ideal for low to medium product volumes. So for your syllabus, like as I told, so we have here PAL 16L8, which has got 16 number of input lines and 8 number of active low outputs. Hence the name PAL 16L8 is being used. And we have the next version of it is PAL 16R8 also. Okay. So we have this PAL. So where PAL stands for programmable array logic, and these are commonly used programmable devices which have got programmable AND array and fixed OR array. Remember this point. So these PALs will be having the programmable AND array and fixed OR array. So because only the AND array is programmable, it is easier to use. So, but not feasible as compared to the PLAs. Okay. So the main point here is, so we have this PAL where we have the programmable AND array and fixed OR array will be used. And for your syllabus, so we have this PAL 16L8, okay, like its architecture along with the implementation and how do we have the connection between the various min terms, okay, and so as to come up with a new expression. Okay, so for that, let me have the architecture of this PAL 16L8. Like as you know that, like we have here 16 number of inputs and 8 number of outputs will be there. Okay, so whatever the diagram, like what we are seeing inside this hashed box. Okay, so this programmable grid, we call it as. Okay, so this programmable grid has got 32 number of vertical lines from 0 to 31, like as you can see here, 0, 1, 2, 3 up to 31 number of vertical lines are there. and we have 0 to 64. I mean, 0 to 63 means 64 number of horizontal lines are there. Okay, right? So we have here 0 to 31 number of vertical lines and 0 to 63. 63 means 64 number of horizontal lines are there. So these vertical lines, okay, so these vertical lines are being connected to the input buffers, as you can see here. So these vertical lines are being connected with the input buffers, okay. So there we can have the complement version of the input as well as the normal input, okay. So these vertical lines, right, are being connected to the input buffers, okay. So for example, this line 0, so line 0 and line 1 are connected to the input buffers, right? There is line 0 like is having connection here and line 1 is having connection here, okay? Yeah, so line 0 is connected to I2, see here. So this line 0 like is being connected to the I2, okay, input line I2, and line 1 is connected to I2 bar. Like as you can see a small dot here, like this indicates the negation of I2. Hence, this corresponds to I2 bar and this line corresponds to I2. Okay, so this vertical line 0 is connected to I2 and again the second vertical line I1 is connected to I2 bar. Okay, similarly line 2 and 3. So line 2 and 3 are connected to I1 and I1 bar. Okay, like here is our I1, right? So this I2, I mean, so this vertical line 2 and 3 are connected to I1 and I1 bar. Okay. Similarly, so we have 0 to 31 means 32 number of vertical lines that will be giving us 16 variables of 16 literals. Okay. So plus 16 complemented version of those literals. Okay, right? So we have 16 plus 16 equal to 32 number of variables like 0, 1, 2, 3 up to 31 means 32 number of verticals are like vertical lines are there. And these vertical lines are able to give us 16 variables plus 16 complement of those variables. Okay, right. So like as you can find here, so we have some information regarding the number of pins used here, right? And the kinds of pins. So what you can see in this architecture of this PAL 16L8. So basically we have here 10 number of only input lines. Okay. So the lines which can act as only input lines are 10 in number, and those lines are I1 to I10. So like as you can see here, I1, yeah, I1 is here and I2 is here, I3 is here, and up to I4, I5, I6, etc. So up to I8, I9, and I10. Okay, so basically we are having I1 to I10 as only the 10 number of input lines, and only two output lines are there. Okay, and those output lines are O1 and O8. So O1, where is O1? Yeah, um, yeah, O1 is here, okay, and O8 is here. Okay, so we have O1 and O8 lines, so which can only act as output lines. Okay, so whereas input lines are only input lines are I1 to I10, and we have two output lines. Okay, and those are O1 is here and O8 is here, and we have six lines, so which can act as so both input lines as well as the output lines. Hence, these are called as bidirectional lines. Okay, so we have six number of lines which can act as both input as well as output lines. Hence, these lines are called as IO lines or bidirectional lines, and those are I02 to I07. I02, where is I02? Yeah, I02 is here, right? And similarly, so you can see the dots here. Okay, so we have a continuation like I02, I03, I04, I05, I06, and I07 is here. Hence, I02 to I07 are the six number of IO lines are also called as bidirectional lines. So regarding this input buffer, okay, information regarding this input buffer. So what I can have, So at the input, so you can go for use of these buffers, and like these buffers can give the variable or the literal plus complement of the literal as well. So for example, I can have, suppose if the input for this buffer is I2 means, so I can have I2 as well as I2 bar. Okay, like as you can see, so for I3 as well. Okay, so for the input buffer, so for the I3 input line, so you can have I3 as output as well as I3 bar. Okay, so these buffers can offer us the normal output as well as the complement version of the input, right? Yeah, so now coming to these horizontal lines. Okay, so what you're seeing here from 0 to 63, and in total 64 number of horizontal lines you can see here. So these horizontal lines represents the product terms. Okay, so at the end of the horizontal line, okay, so we have the AND gate being used here. Okay, so you can see it. So at the end of each horizontal line, okay, so we have the use of the AND gates, right? So these horizontal lines represents the product terms, and at the end of each horizontal line, you can find the use of AND gate that represents that a product term will be formed. Okay, a product term will be formed for each horizontal line. Next information is regarding the, so these let's called tri-state drivers, right? So these symbols are indicating the tri-state drivers where we have the input and the output. Along with that, you can also find here one more line. So this line we call it as a control line, right? So at the output is, so you can have the use of these tri-state drivers, right? So you can see here and like in these places. So at the output, we basically have the use of these tri-state drivers, and the inverter, like the bubble, indicates that outputs are active low, right? So these bubbles is indicating that the outputs are active low, and the outputs are also being controlled by a control line, right? So the outputs are controlled by the use of the control line. That is, the output of AND gate is always the product term, right? Yeah. So again, so at the output part, so you can have the combination of these AND gates to be given for the OR gate. So at the output part, so we have the use of OR gate that is able to combine all the product terms offered by the AND gate so as to form the SOP expression, sum of product expression. Okay, here it is. Like we're using a OR gate, and it combines all the product terms offered by these AND gates and array. Okay, so at the output part, so we have the use of OR gate that will combine all the product terms offered by the AND gate so as to form the sum of product or SOP expression. So in the unprogrammed state, what we have is, so we have something called as fuses, like these cross marks. So what you're seeing here on the screen, right, or on the grid, so we call it as the fuses. So in the unprogrammed state, so we have these fuses, and this X is present at each and every intersection, right, of this grid. Okay. So once the device is programmed, means using these programmable instruments, okay, like it will blow off some of the fuses, right, according to the function what is supposed to implement. So by keeping the fuses and blowing off the fuses, you can go for the programming of the PALs. Okay. So once the device is programmed, means using some programmable instruments, I can go for the program of it, and it will blow off some of the fuses. Some of the fuses will be blown, okay, according to the function what you're trying to implement. Therefore, this X seen in the diagram are connected, and so wherever the X is absent, say here or like wherever it is, okay. So wherever the X is absent means they are not being connected, and wherever you can see the X mark or the cross mark, okay. So these cross marks are indicating that like those lines have been connected, okay. So we have a connection there, okay, and this connection can be made based upon the expressions what we have in your expressions, okay. So once you are familiar with the information regarding regarding the architecture. So let me see the next part of it. Okay, so we have some equation to be implemented. So like I2, I1 dot I2 plus I3 dot I10 bar whole bar, etc. So let me analyze like what do we have this sort of information like to be implemented on this grid. Okay, so you can see this figure. Say, so you can see the first horizontal line. Okay, so this line zero. So we have the fuses at line number 24 is here and line number 31. Okay, so let's say this line will be able to implement I8 and I10 bar. So this I8 line 24 is been connected to I8. See here. So this horizontal line 24, like is been connected to this line, yeah. So first horizontal line, like that is line 0. So this horizontal line 0, okay. So you can see the connection of fuses at the number 24 and at the number 31, okay. So this line will be implementing I8 dot I10 bar. So why I8? Because so this line 24 is being connected to the input buffer I8, okay. Yeah, like this point it is, okay. Like this point, like what I'm showing here is having connection with the I8, right? And I10 bar is available at the line number 20, line number 31, okay. So you can see here I10 is here, okay. So this line 31 is here, okay. Line 31 is having connection with the I10 bar. Here it is, okay. This point is for the input I10, okay. Hence you can have I8 dot I10 bar. Why bar? Because so this negation, because the bubble is being connected to this line 31, okay. Similarly, suppose if you see the vertical line, so vertical line 24, so vertical line 24 is here, right? So vertical line 24 is here and it is connected to I8, okay. So line 24 takes input from I8. Here it is, okay. I8 is here and line 24 is here, right? So this vertical line 24 will take the input from I8. Similarly, vertical line 31 will take I10 bar, okay. Hence we have the product term at the end of the horizontal line, and that will give us I8 dot I10 bar, okay. So this controls the tri-state buffer, okay. So if like suppose if the control signal is active, okay. So for any sort of tri-state buffer, suppose if the control line is active, so then the tri-state buffer will produce the output, right? That is the output of the OR gate, right? So the output of OR gate will be available if and only if the control line is activated. Similarly, if control line is not being activated, means output will be in the Z, means output will be in the high impedance state. So you can understand the function of this control line, okay. So the use of this control line, so for all the tri-state drivers what we have, suppose if this control is active, means I can have the output of the OR gate, and in terms of the SOP expression, sum of product expression. And if the control line is not yet activated, means the output will be in the high impedance state. So now if you see the horizontal line 1, okay. So this horizontal line 1 is connected to vertical line 0 and vertical line 2, okay. Understand this. So this horizontal line 1 is connected to the vertical line 0 and vertical line 2, okay. And this will implement the product term I1 dot I2, okay. I1 dot I2. And if you see the horizontal line 2, okay, horizontal line number 2 is connected to vertical line 4 is here, and the horizontal and the vertical line 31, okay. So this horizontal line 2 is being connected to vertical line 4 here and vertical line 31, okay. So like this particular place 4 and at this particular place 31. So we have a connection of the queues. So this will be implementing I3.I10 bar. Okay, so the output of the tri-state buffer will be I1.I2 plus I3 into I10 whole bar. Okay, so thus we have AOI logic here. Okay, and or an inverter logic is implemented using this PAL16 L8. And here we can implement the combination functions so as to implement the sequential functions. So what we need, okay. So we can implement some it's called combinational networks, combinational designs, as well as the sequential designs. So, but for the sequential designs, we may need some extra number of elements to be used. So, for example, registers. Okay. So at the end of the OR gate, we can go for a use of registers so as to implement the sequential designs. Okay. Like using these registers, so we can implement the sequential functions. So like FSMs. Like FSM stands for finite state machines. Okay, like using the registers at the output end, so we can also implement the sequential functions like so like finite state machines. So now regarding this PAL16R8 output circuit, like in the last figure, like we have seen this AND array. Okay, same thing it is. Like at the end of this horizontal lines, so we have the combination of this AND array. Okay, same block is being shown here, right? Okay, so we have this AND array along with the OR gate to be used, and we have the use of a register here. So where a simple D flip-flop can be used as a register, like having single input D, like along with the application of the clock, and we have two normal outputs of the flip-flop like so it's Q and Q bar. Okay, like this PAL16R8 is nothing but like it's a variant or the one more version here of PAL16L8. Okay, so you can find here the use of a register, like or a D flip-flop can be used as a register, and the output is connected like you can see here the output Q is being connected to the tri-state buffer or driver, like using this register D. Okay, so like using register D is so you can provide the feedback to the AND array. Like as you can see, the output Q bar of active low output Q is being given and like as a feedback to the buffer here. Like using this register D, so you can provide the feedback to the AND array. So this feedback is helpful like in the implementation of the sequential functions. As we told, example for the sequential designs will be the finite state machines. So while implementing the finite state machines, so we can go for the use of this particular feedback. So where the active low output Q will be acting as the feedback that is given to this buffer. Okay, for the tri-state buffer or driver. Okay, so this feedback will be helpful in implementing the sequential design circuits like finite state machines. And see the OR gate. Okay, so like this OR gate will be able to combine all the product terms which are offered by the output of AND array. Okay, right. So you can have this, right? So next is designing with the PALs. Like earlier, like we have seen the structure of a PAL. So now dealing with so these PALs or designing with PALs. So what is a PAL basically? So this PAL is a family of PLDs basically, right? So these PALs like so what we saw on the previous slide. So example of these PLDs are PALs. Okay, so these PALs are belonging to the family of PLDs, semiconductors used to implement the logic function in a digital circuit. So you can say that like these PLs are say like one kind of programmable logical devices or one kind of PLDs, and it has got a programmable or fixed OR plane and programmable AND plane. Okay, like in these PLs, like these have got a fixed OR plane and a programmable AND plane. Okay, and always we have the programmable AND array at the input and a fixed OR plane at the output. So what we have seen here also. Okay, right? So at the end of each and every horizontal line, so we have this programmable AND array, and at the output side, so we have always the fixed OR array. Okay. Yeah. So these PALs are useful for the simple circuit designing, right? And a single package solution having the lowest cost, and you can describe any Boolean equations. And for that, I can go for a use of the HTLs or simple language, so like ABEL. So where ABEL is some kind of hardware descriptive language, where the long form of ABEL is Advanced Boolean Expression Language for programming the programmable logical devices. So you can have the synthesis to fuse the map file used by the programming instrument. So like using some programming instrument, I can have the programming of so these PALs to be done. Suppose if the design is huge or large and if the design is not fitting in a single PAL, means I can go for the partitioning into multiple PALs, or I can use more complex PLDs. So from examination point of view, like they'll be asking you to have the designing of this PL16L8, okay, or like explain the architecture of a PL16L8. So why the name PL16L8, and like information regarding the number of only input lines, only output lines, and how many pins are there, like which can act as the bidirectional pins, and like the manner of connection between the vertical and horizontal lines, and the use of the fuse, along with the use of these tri-state drivers at the output end, okay, along with the input buffers. Okay, like all these things can be explained here. So next regarding the GAL. So this GAL is standing for generic array logic, right? Or it's also called as a gate array logic. Okay, GAL stands for generic array logic. So these GALs was an improvement over the PAL, because only one device type was able to take the place of many PAL device types. So the basic advantage of these GALs are erasable and reprogrammable. So the contents of the GAL can be erased, and again these can be programmed. Again these can be reprogrammed. Hence, it can be used for prototyping and designing changes. It can be more easy. Okay, so you can have more and more changes for the prototype. Okay, hence for that prototyping purpose, you can go for a use of these GALs. So now regarding this particular figure, according to the book, it is a widely used GAL. Okay, so for example, GAL 22V10, right? So this GAL 22V10 architecture is as shown here. And what you can see here, that again we have the same programmable AND array. So what we saw in the PAL. Okay, so the same programmable AND array is still present. Along with this programmable AND array, so we can also have the input buffers we have. Okay, so that the buffer can offer us the normal output as well as the complemented version of the output. Okay, so along with the programmable AND array, so we do find the use of input buffers, and each buffer can produce a normal output as well as a complemented version of the output. So what we have extra in this diagram is something called as OLMC. OLMCs are called as output logic macro cells. Okay, output logic macro cells, like in short OLMCs. Okay, so where the OLMC is nothing but the combination of the OR gate and OR gate or D register, okay, or D flip flop or register, along with the output tri-state buffer. So this combination of the register or flip flop plus the output tri-state driver can be called as the OLMCs. Okay, and on the right hand side, so what you can see here, so this figure is the diagram for a single output logic macro cell. Okay, so the diagram of this OLMCs. Okay, so what you can see here is being drawn here. Okay, so here one OLMC will be something like this. Okay, like here also can see the same parts like as we have seen in the previous figures. So here same parts are used, that is OR gate you can see here. Okay, so we have the fixed OR gate, along with that can also find the programmable AND gate here. Okay, so where these AND gates will be able to provide us the product terms, and all the product terms will be applied to the OR gate, and the output of OR gate will be the sum of product terms. We know that. Okay, so this OR gate will be able to combine the output of so these AND array, and the output of OR gate is connected to this D register or D flip flop. Okay, and output of it is fed to the multiplexer. Okay, so like output of this is fed to the multiplexer. Again, you can find here two kinds of multiplexer. So you can have here like the output of register that is going for the multiplexer, and then the output of multiplexer is fed to the tri-state driver. Here it is. Okay, like as I said, like here you can find two kinds of multiplexers to be used. Okay, so one we call it as the output multiplexer. Here it is, right? And second one is the input multiplexer. Okay, so the below one we call it as the input multiplexer, as I'm showing here. So these two multiplexers are programmable along with the programmable AND array. Okay, so like in case of this generic array logic, right, along with these AND gates, so these two multiplexers are also programmable. And we have got some pins here where SP, so this SP stands for synchronous preset, and this is under the control of clock. Okay, so this SP stands for synchronous preset. Okay, and if SP is equal to 1 means output Q will be equal to 1. And we have AR, right? So this AR is for asynchronous reset. Okay, and this is not under the control of the clock, and it makes this output Q is equal to 0. Okay, and hence we call it as a asynchronous reset. Okay, so where this asynchronous reset is not under the control of the clock, and this can make the output Q is equal to 0. And using this output multiplexer, so you can provide the combined output. Okay, so you can have something called as a combinational output. That is the output of the OR gate. Okay, output of OR gate can be directly fed to the output tri-state buffer, or I can feed the registered output. Okay, or I can feed the registered output or the output of OR gate via the register. Okay, that can be fed to the tri-state driver. Okay, so I can explain this thing with respect to the generic array logic. So the main point here is, along with the normal input buffers and the input pins, so we do find the use of OLMC, where OLMC is nothing but output. What is the long form of OLMC? OLMC stands for output logic macro cells. Okay. So next thing is CPLDs. So where CPLD stands for complex programmable logical devices. So like these are programmable logic devices with complexity between that of PALs and FPGAs. Okay. So the complexities of these CPLDs will be lying in between the PALs and FPGAs, and architectural features of both. Okay, this combines the architectural features of both PALs as well as FPGAs. So basically, so these CPLDs are also the reconfigurable hardware boards. Okay, so where we can have the programming of any Boolean equation as such, right? Almost similar to the FPGA. So you can dump any logical equation into the CPLDs, and the CPLD hardware board will be acting like one. Okay, so this CPLD is nothing but the combination of multiple PALs. Okay, as you can see here, like this dashed box, like what you can see here is nothing but the PAL, and you can have the connection of these multiple, like, or the combination of these multiple PALs. Okay, so you can see through the interconnection network. So you can have the connection of these PALs. Okay, like these combination of like so many PALs have been connected together, like using this interconnection network. Okay, so you can have the connection of multiple PALs through this interconnection network, and interaction with each other will be happening with the help of this interconnection network only. And So you can also see, so we have here multiple PALs and all will be able to interact with each other through this interconnection network. Okay. So we have this something called as M/C. Okay. So this M/C stands for macro cells. Like it is an extended version of OLMC. Like OLMC, like what we have seen in the previous circuit, where OLMC stands for the output logic macro cell. Okay, same macro cell it is. Okay, like these are the macro cells. I mean, MC stands for macro cells, and it is the extension of OLMC, what we saw in the previous figure. But here, these MCs are not directly connected to the output pins. Instead, an MC is connected to the output pin through this IO block. Okay, like all these MCs, okay, are not directly connected to these output pins. Instead, the connection of each and every macro cells, okay, are being connected to the output pins via this IO block, okay, input output block. So this IO blocks is programmable and it can be configured to give the registered output or non-registered output or the combinational output. Okay, remember this point. Okay, so this IO block is programmable and we can have so what all sorts of output. So like it can be programmed so as to give registered output or non-registered output or combinational output. Okay, so these output pins also supports various voltage levels like TTL or CMOS logic. Okay, and we have used so we have so various types of outputs to be obtained. So one is the registered output, second one is non-registered output, and third one will be the combination output. And we can have the output pins to be supporting to offer us so various voltage levels as well. So namely TTL voltage levels as well as the CMOS logics. And so regarding this flash RAM, so this flash RAM will be used to store the bits. And using these bits, so we can configure the multiplexer and AND gate array, okay? And also we can program the IO blocks, okay? Like in this diagram, so we can have the programmable blocks are, so we can have the programming of the multiplexer as well as so you can program these AND arrays and as well as the IO blocks are also programmable, okay? So like regarding the CPLD, like this can be explained with the help of this particular diagram and also mention the use of this interconnection network and the use of this macro cells and the use of IO blocks, right? Okay. So next is FPGAs. So this FPGAs are nothing but reconfigurable hardware boards. We have the main important ingredients in the architecture of FPGA. So what we have seen in the VLSI design subjects as well. Same content can be used here also. Okay, same diagram, same architecture can be used here also. So we have the main blocks involved in the FPGAs are the IO blocks. Okay, IO blocks are also programmable, and we have the use of these logical blocks. Logical blocks are also called as logical elements, LE. Okay, LB or like LB for logical blocks, or we can call it as LE for logical elements, and these are also called as CLBs. CLB stands for configurable logical blocks. Okay, so these LB and LE for logical elements or configurable logical blocks CLB. Okay, all are one and same. Okay, right? So we have this IO blocks like at the periphery of the architecture and in the middle. So we have the array of these logical blocks or logical elements, and we have the use of RAM. Okay, so this RAM will be holding the configuration bits. Okay, so plus the data to be configured or process will be held in the RAM, and we have this programmable interconnect as well. Okay, so we have the running of the interconnection lines like in between these logical blocks or logical elements. Okay, so basically these IO blocks are also programmable, and these can be registered input output or unregistered input output or the combinational input output lines. Okay, so these logical blocks are like these logical blocks can implement the logic function. So for example, I can implement a decoder or a hop adder, okay, like using these configurable logical blocks. And we know the use of RAM. So this RAM will be holding the configuration bits. Along with that, the data to be processed will be held in the RAM. And we do find the use of programmable uh, like so also find the use of this programmable interconnect, and these interconnect lines will be running like in between these logical blocks. Okay, so this logical block of Spartan 2. Okay, so the logical block example, right? So we have the simple diagram to represent the logical block. Like in case of Xilinx FPGA, so Xilinx is the main vendor or supplier of this FPGA boards. And when compared to this logical block, a simple example of this logical block is shown here. And this belongs to the Xilinx FPGA and Spartan 2 family. Okay. So you can see that like this logical block will be divided into slice, okay, like something called as a slice, where each slice is again divided into two parts. Okay. Like in each part, so you can have the use of LUTs. Okay. So this LUT stands for lookup table. Okay, so these lookup tables can accept four input data bits. So for example, G1, G2, G3, G4 are the four input data bits. Okay, so these four bit data can be addressed of one bit location. Okay, right? So like in each part, I can find the use of LUTs, like as you can see here. And these LUTs are nothing but synchronous RAMs, like having the location of its own. And these locations will be one bit wide. Okay, so these LUTs accepts 4-bit data input. Okay, so this 4-bit data input can be the address of 1-bit location of LUT. Okay, so the data stored in 1-bit location is applied as the output. Okay, according to the address applied. Okay, like using these LUTs, so we can implement any function with 4 variables. Like as you can see here, G1, G2, G3, G4 are the 4 variables. Hence, using a LUT, we can implement any function which has got 4 variables. And output of LUT is given to like a block called as carry and control logic. Like this, like say this block can be containing XOR gate and gate to implement the address and to implement multiplexer and to implement the fast carry logic. Okay, so we have the register D flip flop to be used here. Okay, so which can get us the registered output. So here this YB, so what I can see here, so this YB we have, and we have the use of Y output, and we have the use of YQ, right? So we have YB kind of output or Y output of YQ. So what is YB basically? YB indicates the complement of the unregistered output, and Y represents the unregistered output, and YQ is basically the registered output. Okay, so we have the use of a D flip flop or a D register, using which I can obtain various kinds of output. So one is YB, second one is Y, and third one is YQ, where YB is the complement of the unregistered output, and Y is representing the unregistered output, and YQ is the registered output. Uh, Similarly, in the second LUT, like if you see, means second LUT also can implement functions having 4 variables, F1, F2, F3, and F4. And working of the carry and the control logic, so what you can see here is the same, like as we have discussed here also, like in the previous discussion. Like so, like in the first slice, you can find here YB, Y, and YQ, right? Similar to that, like in the second LUT, also can find the output as XP, X and XQ. Okay, so where X and Y are the two different functions implemented here. Okay, so where like here X and Y are the two different functions which are implemented. So like in a single slice of so one logical block of Spartan 2. Okay, so this logical block can implement two functions basically, each function having four variables G1, G2, G3, G4, and second function having one more four variables F1, F2, F3, and F4. Okay. So next we have this IO blocks. Like so these IO blocks will be having the registers and the multiplexers. What you can see here. So the registers and multiplexer controls the output tri-state drivers. Okay, so these the registers and multiplexers are directly connected to the output from the logical blocks. So the output from the logical blocks can flow through the buffer as the unregistered output, and also you can have the output through the register or D flip-flop and through the multiplexer and to the output register, right? Suppose if the tri-state buffer is not active, okay, suppose if the tri-state buffer is not active, means you can accept the input from this same pin. Like here it is. Okay, suppose if this pin is, suppose if this tri-state buffer is not active, means I can also accept the input from this particular pin. Okay, I used to call it as a bidirectional input and output pin, right? And through this input buffer only, input can be accepted through the input buffer, so via the D register. Okay. So next concept is the IC packages. So it's IC packages is so you can have here like so various kinds of IC packages to be used. Yeah. So for example, I can go for the dual link package, IC package, or I can go for small output line package, or I can go for QFP, quad flat package. Okay, so where IC packaging simply refers to the material that contains a semiconductor device. So this IC or the integrated circuit is what you can have. So the actual implementation of the IC on the silicon chip will be having a material, okay, upon the IC, where that the material that contains the actual semiconductor device or the design will be called as a package. So the package is a case, okay, that will be able to surround the circuit material so as to protect it from the corrosion or some physical damage. Okay, so the main purpose of this packaging is to protect the design, okay, say from corrosion or from physical damage, and also the package will be helping us to mount mount these ICs or components, okay, on the PCB. Okay, like using this packaging optionality, so can go for the mounting of these ICs or components right on the printed circuit board. Okay, so this packaging is nothing but the material that contains semiconductor device, and the main function of these packages is to provide some sort of protection, right? Protection for the designs against like effect of corrosion or some physical damage. And this packaging will be also helping us to say fix these component on the PCBs or printed circuit boards. So these ICs are encapsulated or covered in the protective packages, and we do have the use of external pins for connection on the printed circuit boards. Okay, so you can go for either the bonded wire connection or can have flip chip type of connection. Okay, so we have these figures to be explained, and that I'll be taking in the next class. Okay.